So when the White House is your user, how does it differ from any other user?
When the user is the White House, the design philosophy becomes singularly focused on certainty. The primary design question is no longer cost, schedule, or elegance. It is whether any point of failure remains that could surface to the user.
Back in the day, national security was about tanks, aviation, submarines. Today, how has cyber warfare changed the definition of national security?
Before the widespread adoption of IP-based networking, IP Internet Protocol, most attacks required physical proximity. Once global networks standardized on TCP/IP, that constraint disappeared.
Are most governments technologically incompetent? Will AI increase global instability? Is privacy already dead? Is complexity the biggest enemy of security? Should nations develop offensive cyber weapons?
Yes, the best defense is a good offense.
There are many misconceptions from civilians regarding government tech, Area 51, UFOs. So what are the most common misconceptions civilians have about how government tech actually works? اهلا بيكم في حلقه جديده مع جوده من سلسله سباق. الحقيقه النهارده حلقه مميزه جدا. الحلقه النهارده هتكون بالانجلش. معانا مستر جون كيث كينغ، كان ليد كوميونيكيشن انجينير في البيت الأبيض وتشيف جوينتس اوف ستاف في البنتاجون. احنا في جوده مهتمين بالتكنولوجي ومهتمين بالكواليتي في التكنولوجي، وان احنا نوريكم التكنولوجي من جميع البرسبكتيفز. لو انت بتحب التكنولوجي فالحلقه دي ليك، لو عايز تشوف التطور في التكنولوجي برضو الحلقه دي ليك. فايده الحلقه بتاعت النهارده انها هتوريك الفرق بين التطبيق التكنولوجي في الشركات وتطبيق التكنولوجي في الهيئه الحكوميه او في الحكومات عامه. طريقه تطبيق المشاريع هنا بتتعمل بطريقه، هنا بتتعمل بطريقه، هنا الفاكتورز اوف سيفتي اعلى من هنا، بس هنا الافشنسي اعلى من هنا. الكلام ده كله هنتكلم فيه في الحلقه بالتفصيل. زي ما قلت الحلقه بالانجلش، هيبقى فيه ترجمه تحت عشان برضو لو انت بتفضل انك تقرا بالعربي الترجمه متاحه تحت. و introduction سريع عن مستر جون. مستر جون هو الكاتب لكتاب Servant Leadership Women and the Future of Leadership، وفي ارتكلز كتير كتبها برضو هنسيبها تحت في الديسكريبشن، وهنعرض لكم شويه منهم في حته هنا على الشاشه. لو انت مهتم بالاي اي، لو انت مهتم بالتكنولوجي، لو انت مهتم بالافكتس بتاعت التكنولوجي دي على العالم، الارتكلز دي مفيده جدا ليك ومهم جدا انك تقراها. مش عايز اطول عليكم، هسيبكم مع الحلقه. enjoy. Welcome to a new episode of Sabaq series from Joda. Today we are accompanied by our guest, Mr. John Keith King, former White House lead communication engineer, Joint Chief Staff of Pentagon, and author of Servant of Leadership, Women and the Future of Leadership. How are you, Mr. John?
I'm well. How are you, Omer?
I'm doing great. So, Mr. John, we'd like to, first of all, before starting our episode, hear a personal introduction from you.
Really? Well, I'm not sure there's much to say. I am a electrical engineer by trade. I have approximately 40 years of experience across multiple industries, including wireless, heavy U.S. Department of Defense. I'm a U.S. Navy veteran. Some of that's going to come out in my answers. And I've worked for 4 U.S. combatant commands, Indo-PACOM in Hawaii, U.S. AFRICOM in Stuttgart, Germany, U.S. European Combatant Command also in Stuttgart, Germany, and U.S. SpaceCom, Colorado Springs. Probably the peak of my career was working for the White House as a communications lead engineer, so in strategic comms. And thank you for hosting me.
Pleasure is mine. So we would like to start with our first set of questions regarding what it means to design systems where failure is not an option. So the first question would be, what is fundamentally different about engineering for governments versus engineering for enterprises, where we know that engineering for governments is a place, it has no place for mistakes?
Right. Okay. So the fundamental difference is that governments are not optimizing for profit, speed, or even efficiency the way enterprises do. They are optimizing for continuity of authority and national consequence management. In enterprise environments, failure is expensive. In government systems, failure can be destabilizing. That single difference drives everything. I'll give you an example from early in my career. When I worked at Sprint PCS in the late 1990s, we built a scaled test data center that mirrored production. Everything was tested end to end before it ever went live. That model assumes you can safely experiment outside of production. In government and defense environments, that assumption often does not exist. Many systems are treated as continuously live because they support real-world operations at all times. Instead of isolating risk in test environments, risk is managed through redundancy, process control, and human oversight. The approach is not efficient and it is not elegant, but it is rational given the stakes. When the system underpins national decision-making, you trade optimization for survivability. It is a trade-off, not a flaw. Enterprises can accept outages and rollbacks. Nation states cannot. Once you accept that premise, the architecture follows.
So usually governmental projects are more costly than enterprise projects. Or is that a
In
bold
many
statement?
cases, I'm sorry?
Or
Yeah,
is that a bold statement? Yeah.
in many cases, I think that's true. Certainly in defense, it can be more expensive, but it's, again, you're not comparing, in the US, we would say, you're not comparing apples to oranges. You're comparing apples to oranges, not the same to same, right? It's not really a fair comparison. And we're going to address some of those issues you just raised.
So when the White House is your user, or is the user of the system you're building, or a client, how does it differ from any other user?
That's a really good question, Omer. When the user is the White House, the design philosophy becomes singularly focused on certainty. The primary design question is no longer cost, schedule, or elegance. It is whether any point of failure remains that could surface to the user, which is the President of the United States. If the answer is yes, the system is incomplete. That leads to architectures built on layered redundancy, independent of components, and diversity of paths. Failure is assumed at the component level, and the system is designed so those failures are absorbed invisibly. In environments that support US national leadership, survivability overrides optimization. Decisions are driven by consequence, not efficiency. The measure of success is simple. The system works continuously, regardless of external conditions. So that's kind of my answer for that question.
How do you define mission critical in environments where lives, diplomacy, and national security are at stake?
Another good question. I've never thought of mission critical as a label so much as a condition. A system is mission critical when its failure creates consequences that cannot be mitigated in real time by people, policy, or by improvisation. In those environments, failure does not mean inconvenience or delay. It means loss of options. It means that decisions are forced earlier. with less information, and often under pressure. So mission-critical systems are not defined by uptime targets or service level agreements, like in typical data centers. They are defined by consequence. If the system fails, what becomes impossible next? When the answer is diplomacy, deterrence, or command authority, the system is mission-critical by definition.
So, what technical decisions carry the most irreversible consequences in defense systems, for example?
Gotcha. The most dangerous technical decisions in defense systems are the ones that remove the ability to recover judgment. In many technical environments, failure can be rolled back, data can be restored, systems can be rebuilt, and that creates the illusion that most decisions are reversible. In defense and national systems, irreversibility usually enters much earlier at the architectural level. Decisions about coupling, trust boundaries, automation, and dependency chains can lock you into behaviors that cannot be undone once the system is live. When a system is designed so that recovery depends on speed, perfect information, or human intervention under pressure, you've already made an irreversible choice. The safest systems are not the ones that recover the fastest, but the ones that preserve optionality when something goes wrong.
As we know, that governmental projects are conservative. So, how do you balance between innovation with the extreme conservatism required in secure environments?
Okay, that's a really excellent question, Omer. I'm going to challenge the premise of the question, though. Working in a secure environment is not about extreme conservatism. It is about clarity of boundaries. Once you are in a secure space, whether that space is an open secret space, a top secret SCI, SCIF, or any controlled environment, everyone present knows the rules. Everyone is cleared. Everyone knows what can be discussed and how information is handled. That shared understanding removes friction rather than creating it. Innovation does not slow down in secure environments, but it becomes more disciplined. You can move quickly because you are not constantly negotiating trust or exposure. The real balance is not between innovation and conservatism. It is between creativity and control. Security provides the control so that innovation can happen safely inside the boundary. This last bit is really important. The most dangerous environments are not secure ones. They are environments where people think they are secure, but are not.
Mm. So, there are many misconceptions from civilians regarding government tech, Area 51, UFOs. So, what are the most common misconceptions civilians have about how government tech actually works?
Another really good question. One of the most common misconceptions is that governments operate like slow or poorly run businesses. And that is simply not true. They're not businesses at all. Governments exist to provide services to citizens and maintain state functions. Profit is not a governing metric, and efficiency is always subordinate to accountability, legality, and continuity. That reality shows up most clearly in how government technology is acquired. Within the United States, large systems, especially defense systems, are not purchased the way commercial technology is. They are governed by extensive acquisition frameworks designed to ensure transparency, fairness, and political oversight. Those frameworks shape what gets built, how fast it gets built, and how much flexibility exists once a program is underway.
So, till this day, till 2026, Why is secure communication still one of the hardest unsolved problems in modern systems?
Now you're getting into the heart of my career. Okay, so again, I would challenge the premise of the question. Secure communications at the highest levels of government within the United States and the US military are not an unsolved problem. Those systems are designed, deployed, and operated with security as the primary requirement, and they work. Where the problem exists is in global civilian communications, wireline, wireless, and internet-based systems. Those systems are designed first for accessibility, scale, cost, and convenience. Security is layered on afterward. When you try to secure systems that were never designed with security as the foundational requirement, you end up with partial solutions rather than truly secure communications. So the challenge is not that secure communication is impossible. The challenge is that most of the world is communicating on infrastructure that was optimized for openness and not protection. Security works very well when it is the first requirement. It works poorly when it is an afterthought.
Back in the day, national security was about tanks, aviation, submarines. Today, how has cyber warfare changed the definition of national security?
So I've actually seen this in my lifetime. So before the widespread adoption of IP-based networking, IP Internet Protocol, most attacks required physical proximity. If you wanted to compromise a system, you needed access to the facility, the equipment, or the transmission medium itself. Once global networks standardized on TCP/IP, that constraint disappeared. Access no longer depended on geography. Anyone with sufficient knowledge and connectivity could reach systems that were previously isolated by distance. That single shift fundamentally changed national security. Borders stopped being meaningful in the digital domain. Critical infrastructure, military systems, and civilian networks became reachable without crossing a physical boundary. Cyber warfare is not a new conflict. It is a conflict without proximity. It turns remote access into a strategic weapon and collapses the distinction between peacetime and active engagement.
So, from your experience, what is more dangerous today? Data breaches or misinformation?
Another good question. I'm going to reframe the question. The most dangerous condition today is not a data breach itself, but organizations that are unprepared to act once a breach has occurred. Across civilian, government, and military data centers, enormous effort and money is spent trying to prevent breaches, and far less effort is spent rehearsing what happens after prevention fails. Breaches are inevitable. What determines impact is how quickly an organization can detect, escalate, contain, and recover. The organizations that fare best are not the ones that claim perfect security, but the ones with standardized, rehearsed response plans, clear escalation paths, defined decision authority, and practiced recovery problems. Resilience is not a technology problem, it's an organizational discipline.
And how do you think resilience versus prevention in critical infrastructure?
I see prevention as a subset of resilience and not the other way around. Resilience has a much broader scope than simply trying to stop an attack. It includes technical hardening, operational flexibility, and critically, the human element. A resilient data center is not just well defended. It is staffed by people who can adapt when conditions change. That means a workforce that is trained, current on certifications, and continuously improving its understanding of emerging threats, including social engineering. Change is constant. Systems will fail. Assumptions will break, and new attack vectors will appear. The organizations that endure are the ones whose people can recognize that shift quickly and pivot without hesitation. Technology enables resilience, but people ultimately deliver it.
Are modern states currently over-relying on software defenses over systemic design?
Okay, I think that question needs to be made more precise. Software defenses are tools. They are neither sufficient nor insufficient on their own. The real issue is whether security is being treated as a product or as a system. When organizations rely on software alone without designing clear trust boundaries, decision authority, escalation paths, and recovery processes, they are not building security, they are outsourcing judgment. Effective security comes from system design first, architecture, governance, and human workflows. Software supports that design, but it cannot replace it. When something goes wrong, and it will, the system either knows how to respond or does not. No software can compensate for that absence.
So, what keeps you up at night when thinking about global digital infrastructure?
This is a really good question. Global infrastructure itself does not keep me up at night. What concerns me is that much of the world is unprepared for a future in which current encryption methods no longer provide meaningful protection. Current advances in quantum computing challenge the foundational assumption behind today's cryptography. When those assumptions fail, the impact is not incremental, it is systemic. That is why governments around the world are investing so heavily in quantum technologies. Any nation state that understands information power understands the strategic importance of both protecting its own communications and understanding the vulnerability of others. The real risk is not quantum computing itself, the risk is delay. Waiting too long to transition critical systems to cryptographic models that can survive what is coming. In other words, don't procrastinate. Now is the time.
So, why is systems thinking and what is, let me rephrase that. What is system thinking and why is it essential in defense and government technology?
Systems engineering is a disciplined process for defining what a system must do before deciding how to build it. It starts by identifying requirements and capabilities, then decomposes those requirements down to the lowest practical level. So each part of the system can be designed, tested, integrated intentionally. A simple example most people would understand is an automobile. An automobile is not a single machine. It is a system of systems. Braking, steering, suspension, power, electronics, climate control. Each of those subsystems has clear requirements, and they must all work together under normal and abnormal conditions. That way of thinking is essential in defense and government technology because failure rarely comes from a single component. It comes from interactions between components that were never considered together. Systems engineering forces you to define assumptions explicitly, test them early, and refine requirements as you learn. In complex environments, you cannot predict everything up front. Prototyping and testing often reveals requirements you did not know you had. Without that discipline, complexity grows faster than understanding, and that's where high consequence systems fail.
So, from your experience, how do large institutions fail? Is it through technology, people, or governance?
So ultimately, large institutions fail through people. There's no serious doubt about that. Technology is a tool. It executes decisions, assumptions, and priorities that people embed into it. Governance is also created by people. It is a set of rules and processes meant to guide how technology is used. When people make poor decisions, tolerate ambiguity, or avoid accountability, governance becomes performative and technology simply accelerates the outcome. Well-designed governance does not prevent human error, but it can limit how far and how fast that error propagates. Poor governance does the opposite. So while failures may appear technical or procedural on the surface, the root cause is almost always human judgment exercised under flawed incentives or incomplete understanding.
What is the biggest hidden risk in complex systems? Is it human error? Is it technical debt? Is it organizational failures?
In my view, the greatest hidden risk in complex systems is human error. Technical debt and organizational silos certainly contribute, but they mostly determine how far a mistake propagates, not whether it occurs. In sufficiently complex systems, it is impossible to design out human error completely. People operate under time pressure, incomplete information, and competing priorities. That is not a flaw in character, it is a condition of reality. The danger arises when systems assume perfect behavior. When a single routine action can cascade into a system-wide failure, the system is brittle by design. Resilient systems are built on the assumption that mistakes will happen, and they are designed to absorb those mistakes without catastrophic consequences.
When building a system, you tend to write down the risks you're facing and the threats you may face in this system. But how to build a system to face an unknown threat?
It's a good question, Omar. Designing for unknown threats is where systems thinking really matters. You cannot design for what you cannot predict. So the goal is not anticipation, it is adaptability. That starts with layered defenses across hardware, software, and operations, but it does not end there. The human element is decisive. A well-trained workforce, continuous education, and familiarity with stress conditions matter more than any individual control. Resilience is revealed under pressure, not in planning documents. That is why realistic exercises are essential, and this is something that is rarely done. Teams must be tested without advance warning in conditions that simulate uncertainty and disruption as closely as possible. In my experience, this is rarely done well, but if resilience is truly objective, there is no substitute for rehearsing failure before it happens.
As you mentioned earlier in the podcast, that the governmental projects, the main core difference between governmental projects and enterprise projects, that governmental projects, they don't necessarily seek for efficiency, since the error is not an option in that case. So how does redundancy play a role in building a system that should never go down for a government?
It's a great question, and it's very fundamental. Redundancy is a foundational requirement for any system that must not go down. The key principle is this. In critical systems, failure is not an exception. It is an expectation. Every component will fail eventually. Servers, storage, memory, network equipment, power systems, all of it. Redundancy exists to ensure that no single failure is visible to the mission. But effective redundancy is not just duplication, it is independence. Redundant components must fail differently at different times and for different reasons. When redundancy is designed correctly, failure becomes routine rather than catastrophic. The system continues to function while individual components are repaired or replaced. Systems that assume components will behave perfectly will eventually fail. Systems that assume failure will endure. Redundancy is how you turn inevitable failure into routine maintenance.
So, how do you test systems that you hope will never be used in real life?
Another really good question. Effective testing must occur under conditions that are as close to real life as possible. Early in my working career, I worked as an avionics systems and flight test engineer on the F-16 Fighting Falcon. Major software updates were first tested in full-scale simulators where nearly everything was real. Hardware interfaces, avionics, timing, and failure modes, even weapon systems. The only elements simulated were those that could not be reproduced safely. That approach was highly effective at identifying defects early, but simulation alone was never considered efficient. Once issues were resolved in the lab, the software was tested in actual flight conditions at Edwards Air Force Base to expose behaviors that only appear in the real world. The lesson applies far beyond aviation. Systems that matter must be tested progressively, moving from controlled environments to operational reality, because complexity reveals itself only under real conditions. You do not test to prove a system works. You test to discover how it fails before failure carries irreversible consequences.
So, for the upcoming segment, I'll be stating some might say controversial debates that were mentioned in some research papers, and I would like to know your opinion on them. So, first of all, by an article called "The Myth of Cyber Deterrence," cyber threats cannot be deterred the same way nuclear or military threats can. So, is cybersecurity fundamentally a losing game?
Okay. Cybersecurity is fundamentally different from traditional deterrence models because the threat space is not stable. For example, nuclear deterrence works because the underlying systems and capabilities change slowly. The platforms, doctrines, and consequences are well understood and relatively fixed over time. Cyber systems are the opposite. As technology evolves, so do the threat vectors. Every software update, every new dependency, every integration change changes the attack surface. Modern systems and data centers require constant patching to remain functional and secure, but those same changes routinely introduce new, previously unknown vulnerabilities. That dynamic repeats across every hardware and software component in a data center, civilian, government, or military. So cybersecurity is not a losing game in the sense of inevitability, but it's not a game you can ever win. It is a continuous contest, not a deterrence problem. The objective is not permanent security, it is sustained resilience.
So the next one would be that complex systems fail in complex ways. It's an article by MIT Systems Engineering. And the core idea of it was that most large failures come from interactions, not individual errors. And why do we keep blaming people instead of systems?
Okay, so at the most basic level, every system is designed by people. So it is tempting to blame people when something fails. But major failures rarely come from a single mistake. They emerge from interactions between components that behaved exactly as designed, just not as expected when combined. As we've already talked about, complex systems are tested extensively, often under very realistic conditions, such as flight test. But testing can never cover every possible interaction. As complexity increases, the number of unanticipated behavior grows faster than our ability to predict them. Early in my career, working on avionics flight testing, we deliberately performed unexpected actions, not because pilots would normally do them, but to see how the system responded. When avionics systems failed under those conditions, it was not because a pilot made a mistake. It was because the system contained assumptions that had never been challenged. We blame people because it feels actionable and immediate, but resilient organizations look past the individual action and ask a harder question. What about the system made the failure possible?
So there is also an article by Harvard, The Illusion of Control in High Reliability Organizations. And the core idea is that leaders overestimate how much control they really have in complex systems. Are executives dangerously overconfident in their dashboards? So an example of this would be also that that there is also dashboard privilege known risks. So there is known failure modes, known business drivers, known operational risks, but are they really in control since there are the other risks can't be measured through a dashboard or could be random?
It's a great question. I would be careful about saying executives are inherently overconfident, but I do think that dashboards can create a false sense of control, especially for newer executives. A well-designed dashboard provides situational awareness, but it is still only a representation. It is either a snapshot in time or a real-time feed, and neither captures delay, momentum, or downstream consequences particularly well. The real issue with dashboards is coupling. How tightly does the data on the dashboard map to real-world cause and effect? Do changes produce linear outcomes, or do small inputs trigger disproportionate effects? I'm going to give you an example. A useful analogy is a naval aircraft carrier. They're kind of in the news right now in the Middle East. The captain of a naval aircraft carrier has extensive instrumentation and dashboards. But if propulsion is cut, the ship does not stop immediately. It may take 20 kilometers to come to rest. That reality is not intuitive from dashboard displays alone. It is learned through experience. Dashboards inform decisions, but they do not replace judgment. Leaders who confuse visibility with control are at risk. Leaders who understand the limits of instruments and instrumentation, such as dashboards, are far more effective.
So the next point would be an article by Bruce Schneier, Security Theater and the Cost of False Protection. The core idea is that many security measures look impressive, but they add no safety. And how much of modern security is just performance?
It's a great question. The problem is that term is often taken out of context. Bruce Schneier originally used security theater to describe highly visible but largely ineffective measures, like certain airport screening practices that make people feel safer without materially improving security. The concept does not mean that visible security is inherently useless. It means that visibility should not be confused with effectiveness. In complex systems, real security is usually quiet. It lives in architecture, process discipline, redundancy, and response capability, not in performative controls designed primarily to reassure observers. The danger is not security theater itself. The danger is believing that appearance equals protection. When organizations prioritize optics over outcomes, they create blind spots rather than resilience. Serious security work focuses on reducing consequence and preserving options when something goes wrong, not on looking impressive when everything appears normal.
So there is also an article by Oxford, AI in military decision-making, risks of automation bias. The core idea is that human trust automated systems too much in critical decisions, and should AI ever be allowed to make life or death decisions?
Okay, so that is not a technical question. It is a sovereign one. Decisions about whether AI should be allowed to make life or death choices sit squarely at the intersection of national governance, ethics, military doctrine, and law. Those are decisions for governments and societies to make, not for engineers or technologists operating in isolation. My role has always been to ensure that systems behave predictably, transparently, and within the constraints defined by human authority. Whether those constraints should ever permit autonomous lethal decisions is a matter of policy, ethics, not engineering. On that question, I'm comfortable standing on the sidelines.
Okay, so what is the hardest leadership decision you've ever had to make?
This is a really good question. When I was working for the White House on communications between the White House and the Russian Kremlin, we often had difficulty diagnosing problems on the Russian end of the network. There were multiple problems working on technical issues affecting the Russian end of communications. 1, I was not allowed to call the Russians on the telephone. 2, I was not allowed to email them. 3, I was not given access to the Russian network nor knew anything of its configuration. And 4, I only met with the Russians every 3 months face to face. I'm a person that really likes progress on projects. So I did something as the lead engineer that no other lead engineer had ever done in the 20 years of managing this communications link with the current design. I used the direct communications links, the DCL satellite links dedicated to the US president, for troubleshooting the network issues. I crafted a message, sent it to the Pentagon to be translated to Russian, and out it went over the direct communications link, satellite communications. A couple days later, I had a response. Turned out to be much more efficient than waiting months for the next meeting. For me, the hard part wasn't the technical solution. It was deciding when responsibility outweighed precedent.
So, as an engineer designing systems, how do you stay rational when consequences are geopolitical?
I stay rational by being very clear about my role. As an engineer, my responsibility is not to manage geopolitics. That is the job of elected officials and policymakers. My responsibility is to ensure the systems I am accountable for behave predictably, reliably, and within defined constraints. When consequences are geopolitical, emotional reactions and speculation are the enemy of good engineering. So I focus on facts, assumptions, failure modes, and options, nothing else. Rationality comes from discipline, knowing what decisions are yours to make, executing them cleanly, and leaving broader political judgment to those whose role it is to make it. That separation is not avoidance, it is how complex systems remain stable under pressure.
What separates great technical leaders from average ones?
Great technical leaders are not constrained by the decisions or assumptions of their predecessors, like in the last question. They are willing to question the inherited designs and think beyond established patterns when circumstances demand it. In my experience, great technical leaders are also great teachers. They have held multiple roles over their careers, which gives them perspective, patience, and the ability to translate complexity for others. Humility is another defining trait. No complex problem is solved by one person. Strong leaders know how to draw on the depth and expertise around them and are comfortable not being the smartest person in the room. Finally, great leaders give credit generously. They recognize that durable results come from teams, not individuals, and they reinforce that truth by constantly praising the people who do the work. That combination, independent thinking, teaching, humility, and shared credit, is what separates great technical leaders from average ones.
So, and how do you manage teams working under classified and high stress conditions?
Okay. Let me start by dispelling a common myth. Classified environments, whether secret or top secret, are not inherently high stress. In many cases, classification is a function of the physical space and access controls, not the emotional intensity of the work. A minimum clearance is required to enter, but once inside, the work is often structured, methodical, and professional. In my experience working across multiple U.S. combatant commands and the White House, projects were managed using standard project management frameworks. Clear roles, defined milestones, disciplined processes are what keep teams effective, classified or unclassified. Yes, there are periods of high stress, especially when timelines compress or consequences increase, and that sometimes mean long or unusual hours. But those moments are episodic, not constant. Managing teams in these environments comes down to the same fundamentals as anywhere else: clarity of mission, predictable processes, mutual trust, and respect for people's time and professionalism. Secrecy does not change those principles, it makes them more important.
Hmm. And what leadership, what, excuse me, and what leadership traits matter more than technical brilliance?
Okay, so this is my personal opinion. Excellent interpersonal skills matter more than technical brilliance at senior levels. Empathy, tact, and humility are essential because no single person has all the answers in today's data center and systems environments. These systems are simply too complex. One of the most important leadership skills is knowing when someone on your team is struggling but not saying so. Knowing when to step in, when to listen, and when to stay quiet is difficult and critical. Many university engineering programs do an outstanding job developing technical capability, but they fall short in teaching interpersonal communication, professional disagreement, and judgment about when to escalate an issue and when to hold your tongue.
Hmm.
At scale, leadership becomes less about solving problems professionally and more about managing people, trust, and judgment. The human dimension is where many technically brilliant individuals struggle and where great leaders distinguish themselves.
So, how do you build trust in environments where secrecy is mandatory?
It's a really good question. To an outsider who has never had a security clearance, this probably seems like a reasonable question. Very few people in secret and top secret environments know all there is to know. I never let it bother me one bit. Receiving the clearance means you have been vetted extensively for being trustworthy. Simple.
Hmm. So, we've all seen Oppenheimer, and we've all seen multiple movies where the engineer is in conflict with the monster he built. So, should engineers be morally accountable for how their systems are used?
I haven't actually seen Oppenheimer, but I hear it's a good movie.
It's a very good movie.
In my opinion, I do not believe individual engineers should be held morally accountable for how systems are ultimately used. Engineers design to specifications provided by management, policymakers, and customers. They are responsible for building systems that meet those requirements safely, reliably, and as intended, not for determining how those systems are employed. We see this distinction clearly in other domains. Engineers design automobiles, but we do not hold individual engineers morally responsible for how a driver chooses to misuse a vehicle. In rare cases where design flaws contribute to harm, accountability rests with the manufacturer or the organization, not with individual contributors. The same principle applies to complex technical systems. Ethical and policy decisions belong at the governance level. Engineering accountability is about execution, quality, and adherence to defined constraints. Blurring that boundary undermines both ethical clarity and effective system design.
So, in the evolving world of AI and the many theories around AI and how it's used and how it's biased or not biased, is technological neutrality a myth?
Technological neutrality is a myth at the global level. Technology is designed, governed, and deployed by societies with fundamentally different ethical frameworks, legal systems, and risk tolerances. Those differences inevitably get encoded into data, algorithms, and operating assumptions. The moment a system defines what it optimizes for, who it serves, or what it is allowed to ignore, neutrality disappears. What we often call neutral technology is really just unexamined local values being projected globally.
So, at what point, or even should an engineer refuse to build something, and if so, at what point should he refuse to build that thing?
So my answer is going to be my personal opinion. An engineer should refuse to build something when they can no longer claim plausible distance from its consequences. Early in a project, intent can be ambiguous. As systems mature, that ambiguity disappears. When the purpose, impact, or misuse potential becomes clear and it conflicts with fundamental safety, human dignity, or the engineer's professional duty, that is the line. At that point, continuing is no longer engineering, it is complicity.
In the world of big data and internet and smartphones and social media, how do you think about surveillance versus privacy?
This is a great question. I am personally private, and I am not instinctively pro-surveillance, but I am also not naive. I have worked in environments where surveillance was necessary for safety and continuity. Sometimes it was visible, sometimes it was deliberately invisible. The real issue is not whether surveillance exists, it is whether it is bounded, accountable, and purpose limited. Surveillance without limits erodes trust. Privacy without exceptions can undermine security. The engineering challenge is designing systems where neither side is allowed to dominate by default.
From your personal opinion, do you think society is sleepwalking into a world it doesn't understand technically, with the AI growing rapidly and all what's happening around?
Society is not sleepwalking into a world it doesn't understand technically. It is already living in one and has been for some time. The real issue now is that the systems are moving faster than our ability to govern or explain them.
Who should regulate advanced technologies? The governments, companies, or engineers themselves?
Another really good question. In advanced technologies, engineers always set the initial boundaries. They define what is technically possible, and in my experience, they generally act in good faith within real constraints of time, data, and incentives. But engineers are not oracles. They cannot fully anticipate how systems will scale, be repurposed, or misused. That is not a failure. It is a limitation of foresight. Companies operationalize those systems, often optimizing for speed or advantage. Governments, however, are the only actors with the legitimacy to set societal boundaries through governance, law, and ethical frameworks. The problem is timing. By the time governments intervene, some damage has already been done. The challenge is closing the gap without freezing innovation. Regulation works best when it anticipates capability, not when it reacts to harm, and that's often the case.
So the next segment will be fast Q&A questions, which we will respond to it by only yes or no, preferably. Of course, you can respond however you want, but preferably for the sake of the show, we can go with yes or no. Is cybersecurity ever truly solved?
No, change is constant, ergo cybersecurity is never truly solved.
Are most governments technologically incompetent?
No, the US government, the only one I have experience with, has people who are highly competent, people who are incompetent, and everything in between.
Will AI increase global instability?
No, I do not think it will have an effect on global stability. It is being heavily researched virtually everywhere. I do not see that as increasing instability.
Is privacy already dead?
Unfortunately, yes. In my opinion, privacy outside the home, and in some cases inside the home, has been dead for a long time, and it's a trend which will continue.
Is complexity the biggest enemy of security?
No, the biggest enemy of security is people, whether intentional or unintentional.
Should nations develop offensive cyber weapons?
Yes, the best defense is a good offense.
Is open source software a national security risk?
Yes,
Will quantum computing break modern security?
yes, without a doubt.
Is digital sovereignty, is digital sovereignty realistic?
Yes,
Can any system ever be fully secure?
no.
Okay. Now we can go back to answering the long answers. What should young engineers learn that universities don't teach?
In my opinion, more humanities classes, psychology of human behavior, how to handle conflict, and negotiation skills.
What mindset is more important than technical skills?
In a word, focus.
By focus, you mean discipline?
I mean, so it's something I use in my own work. I mean, focus. I mean, you have to be able to focus on the problem set, what you're working on, and eliminate all distractions. And if you can do that consistently, you can deliver stellar results. But it's very difficult because in our current working environment, there are tons of things that can interrupt your day. But if you're able to structure your day so that you can focus for extended periods of time, and you do that day after day after day, then you are going to be a superlative engineer. And that's what I've done in my career.
How should engineers prepare for ethical dilemmas?
This is really a good question. Personally, I do not think a person can prepare for ethical dilemmas, but I assure you they will happen.
So what does career success mean in national service?
Career success depends on the individual. I cannot give a generalization.
Maybe because usually or from an outsider point of view, when we think about people working in the government, we see that career success is jumping up the ranks.
Yeah, I appreciate that point of view, but from my point of view, it really depends on the individual. You can have individuals which have never advanced the government service levels and still be excellent in their roles. They just don't like the added responsibility of management. And I never really had a problem with that. And then you have some people for which, advancing, they're called grades, pay grades. They go 1 through 15, and then there are 4 above that, but those are executive. And for a lot of people, that's the ultimate. But the system compensates people both on advancing vertically in the management chain and also time and service, just like the U.S. military does. So if you're happy being in your grade and you're an expert because you know your job, that's perfectly fine. So when I say it depends on the individual, it really does. Me, myself, I enjoyed advancing up, and but
And you
it's not
surely
for
did.
everyone. Yeah, it's not for everyone.
So what mistakes do ambitious engineers make early in their careers?
We kind of already covered this, but I would say the interpersonal skills are as important or more important than technical ability. So most universities do a really good job of teaching engineering, whether it's petrochemical, civil engineering, in my case, electrical engineering, mechanical engineering. Those programs have been around a long time. Yes, they are constantly changing and adapting, but they're usually with a university degree, you have to take some humanities courses. But I've never seen interpersonal skills or handling disagreement. And there is a lot of disagreement in engineering between engineers in solutions. And handling disagreement is very, very important to be able to do it well and negotiate well and stay professional. And those are not courses that you see at universities. I've never seen them.
If I may add my personal opinion, um, I think dealing with young, fresh engineers, the biggest issue is that they tend to be in a rush to finish the task that maybe it compromises the quality of the task.
Yeah, it certainly can be the case, but that's also a function of management and their time constraints. So um, and
Hmm.
they don't operate in a vacuum.
Yeah, true. Maybe they want to prove to their management that they can do it quick, you know. So, how do you want your work to be remembered?
So it's an interesting question, and it's probably not apparent from people who look at me or what I've done in the past, but I believe that I'm a simple person, really, and I have loads of humility. I would like to be remembered as one person, one part of a team that made a difference. It's the team and the team members that matter more than the contribution of any one person, at least in my opinion. That's what matters.
Mr. John, any last words?
This is a lot easier than I thought it would be. So I want to thank you for being an excellent host and for putting up with my numerous questions before we ever got started. So I don't know who your audience is, but you've done a great job, Omer.
Thank you so much. And it's a pleasure for me having you on the podcast. And I happily answered all your questions, and I would answer more if you asked more.
Well, we can do it another time.
Mr. John, thank you for your time, and hopefully it will not be our first and last episode. We will do part 2, 3, and more if you are willing to.
I'm willing.
Me too. Okay. Thank you, Mr. John. Thank you for your time.